Assalamualaikum warahmatullahi wabarakatuh. My name is Afifah binti Asmawisha, and today with my group members Amir Hazib bin Tajuk Arif, Muhammad Haikal Fitri bin Muhammad Adin, and Nurin Alia binti Amir Ajra, we are going to present our topic, which is piping and instrumentation diagram, commonly referred to PNIDs. This presentation is a requirement for our DPC 50192 Instrument Engineering Drawing course under the guidance of our lecturer, Sir Muhammad Afif bin Muhammad. Today we aim to give you a comprehensive understanding of PNID, what they are important, and how they play a crucial role in engineering process. While my part will cover the foundational knowledge, my teammate will later elaborate on the technical aspect, including how to create PNIDs and their applications in different places of plant design, construction, and operation. So now let's begin with the basics. What is a piping and instrumentation diagram, or what is PNID? In simple terms, a PNID is a detailed graphical representation of plans of process flow. It includes not just the piping but also the equipment and instrument used to monitor and control the process. Now, why are PNID is so important? These diagrams are the backbone of industrial process design. They are used throughout the life cycle of plant, serving several purposes. During the design phase, they act as blueprints, helping engineers conceptualize the process and ensuring that all components are accounted for. In the construction phase, they guide the building of piping systems, instruments, and equipment. During the operational phase, they provide operator with a clear understanding of the system layout, making troubleshooting easier. Finally, the maintenance phase, they assist technicians in locating equipment and understanding interconnections for repairs or upgrades in relation to process flow diagram. PNID are closely related to process flow diagrams, or PFD. While PFD offer a high-level overview of the process, focusing mainly on flow and major equipment, PNID dive into the finer details. They provide information such as a pipe size, instrumentation specification, and safety mechanism, making them indispensable for engineers. Now we understand what a PNID is and why it is so important. Let's look at the elements that make up this diagram in the next slide. A PNID is not just a random collection of symbols and lines. It is a structure diagram that includes piping details, general safety requirements, detail on control and shutdown of equipment, and lastly, information on when to start operating. Firstly, piping details. These cover pipe size, types, and specifications. Instrumentation is instrument used to measure and control variables like flow, pressure, temperature, and level. For safety requirements, information on measures to ensure safe operations such as alarms and interlocks. For control and shutdown mechanism, it shows details on how equipment is controlled and the emergency shutdown protocols. And lastly, the operating procedure, guideline on when and how to start or stop the process. Now for the next slide. An important part of understanding PNIDs is the instrument tag or tag number. Let me break it down. The first letter in the code identifies the variable being monitored, such as FTLP, which is F for flow, T for temperature, L for level, and P for pressure. The second letter indicates the type of control device used to control that process, which is T, V, or C. T for transmitter, V for valve, or C for controller. The number that follows is a unique identifier for that specific instrument. For example, a code like FT101 means a flow transmitter numbered 101. Lastly, in the right side of this slide, a visual representation of instrument locations. PNID also use line types to show the location of instrument. So if there's no line, it means the instrument is located near the process equipment, easily accessible to operator. Or a simple to understand, if there is no line in circle, it means it mounted in field or plant. If a solid line, that means the instrument is located in control room, making it accessible but remote from the process, which is in the simple understanding. If there is a solid line, the equipment is located in control room. And then the last one, the dotted line represents an instrument that is not directly accessible, such as being behind the operator. By including all these details, PNIDs help operators and engineers work more efficiently. They make it easy to understand how the system functions, enable quicker troubleshooting and safe operations. This concludes my section of the presentation, which is focused on the fundamental of PNIDs and their components. Now I will pass to my teammates who will take you through the steps of creating PNIDs. Thank you. I pass to Muhammad Haikal Fitri.
Thank you, Afifah, for your explanation. As for the next slide, we will talk about how to read PNID. We will take a look at PNID code format. The first letter of the code identifies the parameter that are being controlled or monitored, for example, flow, temperature level, or pressure. The next letter is used to define the types of control device being used, for example, transmitter, valve, or control. The number refers to the logical number. As we can see at the picture, we have FV, which is flow, and valve. 01 is number 01. Okay. The next is PNID instrument location. If there is no line, the instrument is located in the field near the process and operator. And if there is solid line, the instrument is located in a control room, accessible to the operator. If there is dotted line, the instrument is not directly accessible. As we can see in the picture, there is no line, solid line, and dotted line. Let's go for the next slide. The next slide, we will talk about example of a PNID. We have temperature control, a piping and instrumentation diagram. PNID is a detailed representation of a plant process flow showing temperature control loop, highlighted in the yellow above. The solid line going from the tank to temperature transmitter 102 indicate that it is physical connection. Likely, this is a thermocouple inside a thermocouple well. Essentially, this is a small pipe with one cap and which is inside the tank and is connected to a converter which translates its signal to an electrical signal. This control is connected to the heating pad, so when the temperature in the tank need increase, the controller will turn the heater on. If it need to maintain or decrease the temperature, the controller will turn the heater off. Equipment and instrument used to control the process.
Okay, thank you. So let's move on to application of a PNID. First is design phase. Assist in conceptualizing the layout and ensuring all necessary components are included in the process design. Next, it's construction phase. Serve as blueprint for constructing the piping and instrumentation system. After that is operational phase. Provide operator with a detailed understanding of the system layout and control process, aiding in effective operation and troubleshooting. Last is maintenance phase. Guide maintenance personnel in locating equipment, understanding interconnection, and performing necessary repair. So next, I will explain about this difference between PFD and PNID. For aspect purpose, PFD is provide an overview of the main process flow and major equipment, and for PNID offer a detailed layout of piping equipment and instrumentation. So next aspect is level of detail is for PFD, less detail, focusing on primary flow and main component. And for PNID, highly detailed, including instrument, valve, and specific control. For instrumentation, PFD is minimal, usually only key control point. And for PNID is comprehensive, showing all instrument, sensor, and control loop.
Thank you, Nuring, for your explanation. Now let me continue. My name is Ame, and I will tell you about the steps and tips for creating a PNID. So the first step is to define the scope of the system. This is to understand the overall process. What is the system's goal? Secondly is to identify the inputs. Are they manual or automatic? Where are they entering and exiting the system? Okay, next, step 3. Step 3 is to identify the outputs. This step is to identify the end product and what's needed to achieve it. Step 4, list all equipments. This is for note all devices, control elements, piping, and equipment involved. Step 5, define component relationships. So determine how components interact. Are they compatible or not? Step 6 is to create the flow. Start at the beginning or end, working step by step through the process. Step 7, add details. In this step, we include specifics like pipe sizes, measurements, and instrument details. And lastly, the last step is review for efficiency. We need to review and check for bottlenecks or areas that could be optimized. So, in conclusion, a piping and instrumentation drawing or a PNID is a vital tool for designing, operating, and maintaining complex process systems. It provides a detailed visual representation of all equipment, piping, and instrumentation as well as their interactions within a process. PNIDs are essential for ensuring safe, efficient, and smooth operation as they guide engineers, operators, and maintenance teams in understanding system layout, control, and safety mechanisms. By clearly detailing each component and its role, PNIDs help streamline troubleshooting, facilitate system upgrades, and enhance communication across engineering disciplines. Okay, that is all from us. Thank you for watching, and we'll see you next time.